So now after the cake, we can continue. And well, I forgot, but there are some more slides which I forgot about, but it's okay anyway. There are only 2 more mitigations left. I know it's quite boring, but I will try to be quick with it. One of the last ones is for relocations read only. And this mitigation, basically what it does is forcing that when dynamically linking a binary, you used to link against libraries which they have symbols, etc. And they used to be resolved on runtime. Okay, the first time you are going to call a library or a symbol, it will look with a helper function for the symbol and then write it in a memory area for making the jump, etc. So what this protection does, is making that area read-only and resolve that symbols during the startup of the binary. So you won't have to, you won't be able to overwrite that memory area. To enable it is used by using these flags. I think I tried it in 64 bits and it wasn't working. I don't know why. But in 32 bits, it's still working. So, well, basically makes some of the sections of the binary, they map them in read-only area. So, how you can deal with this? Well, this is not a big deal because this was a niche technique which was used mostly for format string. But it's not an stopper. I mean, if you have a format string, you can still write anywhere in the binary. There are usually plenty of function pointers to overwrite, or many things that you can overwrite. So this is not a real thing. They made it to try to stop mostly format strings, or one technique which was kind of famous back in the day, but nobody cares anymore about it, probably. The last one is Fortify Source, which is a compilation. It's in compilation time, and one of the things it does is replacing insecure functions like memcopy, memmove. Those are fake. Sprintf and etc. with a secure counter version of those functions. Okay, to enable this protection, you have to use this, and when you use 2, it will use optimization level 2 also. So basically what it does is, you have here, for example, a memcopy, and it will add an extra argument with the size of the destination. So whenever it knows the size of the destination in compile time, it will add it as a 4th argument. So if you try to go over that limit, it will throw an alert or stop it or whatever. It also works for format strings, and whenever you use, well, one of the things that you must know is that when you are using memcopy over a dynamic memory area, the compiler doesn't know how long or the size of the destination. So this doesn't apply for dynamic memory areas. The compiler cannot do that. So, and well, the other things that it protects is format strings, blocking the n specifier, so you cannot write the count of bytes written in the screen. You cannot write it to a pointer in the stack. And also, whenever you take positional parameters, which are set with $sign, it will force you to pop every argument in the stack. So if you use $, you will have to pop the arguments in right order. Also, this protection only applies if the format string is located in a dynamic memory area. Okay, if it's a static or read-only memory area, this protection doesn't make sense, so it doesn't even apply. With this protection, reading and writing a random memory with format strings is successfully stopped. So, well, how you can deal with this? There is an old article crack, which was a way to overcome this format string protection, the part of format strings, which I don't think it works anymore, but back in the day it was cool. And well, when the destination of the copy is in heap, as I said, the compiler cannot recalculate the size, so this mitigation doesn't work. And also it's still possible to cause buffer overflows whenever you are copying in a loop or things like that. So it's not magic protection for all. Anyway, it's one of the best because, in fact, it stops the attack. It's not like address randomization or many other protections which only try to make it harder. This one actually stops them from happening. And well, now I guess comes the part that everybody was waiting for, which is how to use Radare for exploitation. Okay, there are one of the things that you like to do when you are exploiting many times is looking in memory or examining memory. And for that, many times you want to search. You want to search for a string. You want to search for a special opcodes, or this is the same, but well, the first one will assemble the instruction and search for those bytes, while this one will make a disassembly and look, let's say, for the strings. And also you have /r, which will search for rope gadgets. Whenever you are searching, you can use these two evaluable variables where you can define the start and the end of the search. So you can define the range where you want to search, or you can also use some pre-made ranges to search it. So, for example, if you use searching IO section exec, it will only look for sections of the binary which have executable permissions. For example, if we are looking for rope gadgets, we don't want rope gadgets in memory pages without execution. So we have raw, which is basically the normal search, the block file, IO maps. Basically, the IO are the ones which are related to the binary itself, while the DBG ones are related to memory maps. And as I said, you can say only memory map with executable or only memory maps writable or whatever. Also, Radare comes with RayGG. I don't know how to say it in English, not even in Spanish almost. But and this couple of tools can be used for, it's a good helper for shellcodes. Okay, so for example, here it will build this ASM file. It's not a real assembly file, it's just opcodes. It will translate the opcodes to binary. It's like RASM. Well, it's not a full assembly compiler. It will only translate. You don't have to specify sections. You don't have to do anything but opcodes. And it will translate it to 32 bits on Intel architecture. And with this, it will output a C format, like C escaped strings. We can also, for example, build a whole shellcode with a proper assembler compiler, and later take that assembly and translate it to with the Sid with the set flag. You can translate it to CO2, to a C string. So you can open any binary file and translate it to C escaped string. Okay, this will execute. You can also use it to try shellcodes. So you have a shellcode in a file, you can open it, and with X, you will execute the shellcode. Many times you want to try it, with X, it will execute the shellcode itself. With L, you will list available shellcodes because it comes with several pre-made shellcodes. And with L, you will list them. And for example, here we will be making a basic bin bus or bin SH executed on xb syscall and print it in C output. For example, let me see. You see, this will be the typical Beam bash shellcode which executes Beam bash. We add the set, it outputs escaped C string. And if we want to test the shellcode, we can put X and it will execute the shellcode itself. Okay? You can open any other files and execute, and it will execute as a shell. So, well, we can also use it to build payloads. For example, with this, it will build a pattern with 20 node codes. Then it will, what the fuck was it? Okay, it's just append an next string. And also at the byte 10 of that string, write this. So, well, we will see later. There is also another helper.
One question. Could you explain a little bit what is exit? Last exit.
It will execute the shellcode itself.
So the -I execute, what is exactly? Is it predefined?
Oh, I can. Yeah, there are predefined shellcodes which come with RayGG. Actually, it only has exec, but you can add. You can add more. But actually, it only has that one. Yeah, you fucked it up. It was a secret. Anyway, you also have another helper, which it's kind of a compiler, where you can write C code. Many of you may like it, where it will only translate syscall equivalent calls to assembly. So if you want to make a quick and dirty shellcode, as you can see here, there are no includes. The descriptor is written by fire or whatever you want to say. And as I said, you can only use functions which have a directly equivalent in a syscall. Write, read, fork, open, close, whatever. And it will generate a shellcode for you. You use RayCC, the architecture you want, the bits. This will be the operating system and the file with your CTC file, with your CTC code, yeah. And it will generate a shellcode. Not the best shellcode in the world, but sometimes it works, and it's quick. So it's nice. Also, another tool that you will be using a lot while exploiting, mostly for CTF, something like that, is r2con. In English, it will be r2con. Well, it provides with many options to control the execution of the binary. Okay, mainly for control input and output, or standard input, the standard output, or the arguments for the binary. So with args from 0 to whatever, you set the arguments for the program. With listen, you can bound your standard input, output, and error output to a socket. Or you can set them, I think an E is missing in here, but it will be used to set up environment variables. And also, as I said, std in and std out to replace the descriptors of the program. Also, well, it provides with many other options, and there are, when you set a value for any of these variables, there are some prefixes. If you use arroba, or it's in English?
At.
Okay. If you use at, it will read the contents of the file and put it in the variable. If you use quotes, it will escape any chars. If you use exclamation thing, it will execute the file and put the output of the execution. This will be writing an X pair, and with this you will be writing 3 times the pattern that you write after the ads. There are a couple of ways to load the Rarun profiles. One of them is when you execute the Radare, you can use the environment variable, the valuable variable EVG profile and point it to your Rarun file. Or if you are already inside the cell, you can set it the cell, the same EVG profile, and don't forget to reopen the file, so it will load the profile, the new profile. Here you have an example of one of those Rarun scripts. The program you want to execute, which is not mandatory. The argument 0 will be 10. I don't know why, but the std in it will be taken from the standard input will be taken from the file foo. Well, it will be executed under this directory. Blah blah blah. So also another thing that you will be doing a lot is examining the stack. Whenever you are exploiting or plugging, you will be examining the stack a lot. And one of the hidden commands which is really useful is pxr, which, as you can see in here, we are printing 8 entries from the stack from ESP. And here, by the color, you can know if the permissions of the memory area where that address points to. Has read, write, and also the flag EBX is pointing there, or EAX. Also, for example, this other variable is in the stack, so this address is from the stack, and it's ASCII, and its contents is this from that address. And after that, it's all zeros. Here is a better example. For example, this is checking a ROP, which is already in the stack. Okay, so you use pxr to examine the stack, and because it's red, you will know that it has execution permissions. And it will also disassemble the first opcodes in that address. So the stacks, the address in the stack are these ones actually, and all this is extra information about what is in those addresses. For example, next you have these are the environment variables which were next in the stack, and it detects that it's blue, so you have write permission in there, and they are string, so they print it. So it's quite useful to examine the check it. Also, for looking for ROP gadgets, well, this is basically a cheat list, but it's all with /r. With /r, you will get all in a line. You can use regex or a string filtering, and with J, you will get a JSON output. For example, one thing that happens in Intel architectures is that opcodes are from variable length. Okay, it's not the same. For example, here is a disassembly from Spark, and you can see that all the instructions are 4 bytes, and they have to be aligned. If you try to execute an instruction which is not aligned, it will crash. Okay, but in Intel, as you can see, its instruction, they are multiple, they are variable size. So whenever you take these 6 bytes or 7 or whatever, it's not the same as if you only process these 2, or if you process these 2 or whatever. So this instruction, depending on where you start analyzing it, it will mean different opcodes. So that's one of the advantages of Intel, that will generate many more ROP gadgets than other architectures. Next, for building ROP gadgets and also bus setting radar and using using these commands as I showed you. I made a graphic interface so you can build your own ropchains more easily than by searching them with grep or whatever. So you can, I will show you a demo later. If you want to install it, you just have to clone from GitHub, npm install. It uses Node.js, so you will need Node. npm install will install the dependencies, give it execution permissions, and copy it to a path where you have in your path environment variable. And to use it, just use rarop and the binary which you want to look for gadgets interface. No, I should have done a r2pm package, but I didn't. Maybe another day, I don't know. But yeah, I should. Also, I also did another helper for Radare, which is called Cheetah. I don't know, many of you won't understand this joke, but how many of you know Mona from Corellan Immunity Debugger? Okay, whenever you say Mona in Spanish, to my mind it comes Cheetah, because in Spanish it's La Mona Cheetah. So he has Mona and I have Cheetah. Okay, it's a quite simple helper, but it does the job. It has a few features like generating patterns or writing it in memory and then looking for them. Generate files to prepare the stack to emulate a rope chain. It can also convert rope chains to C, Python, or plain text. It can also help you to exploit format strings. It can also help you to search for jumps. It can also help you to search for stack pivots for ropes. So some basic information about security in the executable, convert those nasty addresses to little endian, which everybody hates to swap, and well, and show the help, which is always used. Almost the same applies. It's also Node. So you just have to clone npm install to install the dependencies and give it execution permissions and put it in your Radare prefix. To use it, you just have to call dash !5 cheetah and one of those commands. I will show you more. So now you see even Dodge is impressed with the Radare capabilities of exploitation. And well, I guess that now I will show you some exercises or some demos. If you want to do them, they are on Radare or GitHub. Okay, not Radare GitHub. It's Radare org. And it's okay, this one. This one, 2016, trainings, demos exploitation, and you have exercises here, okay? Just in case you want to try them or whatever. I'm using Debian stable, so it might vary. If you don't recompile the binaries, well, this one is 64, but the binaries are most of them for 32 bits. So if you don't recompile them, the addresses of the binary itself will be the same, but your libraries will be different from mine. So well, just to keep it in mind. And well, let me see, because okay, we will start with the basic Sid, which is so fucking boring that nobody cares, but we have to do it. And well, we have a very basic Stack Overflow. If I can find it, this somewhere. Okay, so it's this one, the simple one. And well, if you look for the code, as you can see, there is a call to the dummy function with an argument, and it just makes a string copy of it. So it will clearly overflow those 64 bytes if you write more than 64 bytes in the argument. So it's quite lame. To set up this, you will need to disable address layout randomization, and you will need also to enable executable stack. Okay, so I will do that. And now please try your exploits against me because I have disabled stack randomization. Okay, and I think the exec stack the query from simple Bob, it's already enabled. So with here, let's open it with Radare. If you remember that, the overflow was a dummy function. So if we examine dummy function, ¿estás troleando? ¿No ha abierto el fichero? What? Ah, ok, sim dummy. Gracias, Laura. Ahora he entendido lo que decía. Okay, so here you can see, well, all of these will be 32 bits, but the only difference in here with 64 basically will be that arguments to function will be passed by registers instead of the stack. But if we get the arguments, they are in reverse side when you are pushing them. So this will be the first argument. This will be the second argument. Okay, and just in case that you don't remember what a string copy does, you have the first argument is the destination and the second argument is the source. So if we look at the first argument, which is AIX, it's a pointer from base pointer, base pointer, less local 48, which is this one, and is 48 in hexadecimal, which is exactly 72 bytes. So we have 72 bytes until we fill or until we overwrite the base pointer. After that, we have 4 bytes for overwriting base pointer and 4 more to overwrite the return address. So we will have 72. I will use the calculator because I cannot. I was joking, just that you can see it. Okay, so this is the offset up to base pointer, 4 bytes to overwrite the base pointer, and 4 bytes to overwrite the return address, which give us 80 bytes. So one of the things we can do now that we know how long or how much we have to overwrite to click. Está grabado. Ah, no creo. Si no era el Free Porn Day, no tengo nada de travestis. Lo prometo. Si había algo, no era eso. Entonces, okay, exercises. One of the things we can do is use RAG to generate the payload. And let me search for this one. So we know it's 80 bytes, we said, so we use P, and for knob codes, 80. And well, it's not that big. it will generate 18 opcodes. If we add set, it will escape it as a C string. So right now we are already overwriting base pointer and also return address. But we want to point the return address to somewhere. Okay, so okay, we can add, instead of 80, I guess we can use 76. And at the end, add the address of, okay, I'm gonna stay now.
Can you translate that?
I have here my notes. Okay, so we will use 32 bits Intel generate the output in. Okay, it is an obsolete. And generate C output, a lot of knobs, and at offset 76, which I was saying you before, we want to write an address in the stack, and with I, we will add an execute shellcode at the end. As you can see here, it's everything knobs, and here at the end we have the shellcode, and here in between we have the address, which we said we want to the return address, which was at byte 76. So whenever you do that, you can generate a room file. Sorry for this, but this terminal is small. And you can add here, we want to execute the program simple above. Also generate cores, if you want to generate a core file in case of fail. And for the first argument, we want to add the payload that we generated with RayGG. So you just have to do exploit core. Okay, this is expected because this was done on my desktop machine, not in this box. And this box has different environment variables than my local box or my desktop. That's one of the problems with when you are exploiting a stack and you are using fixed addresses. So we can debug. We load our profile, the header profile igual our run script was called run, this one, debug, and the file itself. Now it will be running the exploit, or the exploit, excuse me, the binary with the argument we have in that script file. This will be running actually. This one of them will be loading this. And well, let's put a break just before the return in the dummy function. We want to set up a breakpoint in here just before it will pop or overwriting return address. We continue. Now we are in the breakpoint before return of the dummy function. If we check the stack, you can see that it will pop our address, and it will put it in the program counter. And next, there are all knobs. So we can jump, for example, around here, and it should work. Okay, so let's say instead of this address, which was from my old box, we can use this one. Let me save it, because with this so small desktop, I cannot put on. And well, just so you can see, I will show you that what I'm talking about. If we check the stack, which is mapped in between these two addresses, and we go to the end of it. Okay. We are at the end of the stack. This is the end of the stack. And as you can see, the first thing, well, not the end of the stack, actually it's the beginning of the stack, because the stack grows upwards. And you can find here is my environment variables. Okay, this is all my environment variables. After that, you will find the arguments for the program, also the name of the program you are executing. Okay, this is the arguments with which we made, the knobs, the shellcode, just after the environment variables. So whenever, even if there is no address randomization, etc., jumping to a stack address is a really, really bad idea, because the stacks in the address in the stack change a lot just because environment variables or any other thing. So it's not a really smart idea to do that, but well. So let's generate a new payload, decent terminal. So instead of this address, yeah, no, sorry, it's because I cannot copy the payload if I do that in a smaller terminal. So it's basically the same I showed you later, but I'm just changing the address. Okay, I'm just changing this address because I want to jump to another address in the stack. Okay. You know, if I do this in the other terminal, I won't be able to copy it. Well, I can send it to a file, but so now I can open again my r2con file, which is already open here. Okay, and I say the first argument I want this. Okay, now let's save and try, which may fail because yes, I file. Let's use change. Let's just add some more bytes instead. No, maybe my stack is not executable. That's what it is, I guess. Because if I I don't know where the farm comes in. Always Valare. I will. Okay. Let's make the breakpoint in the same place than before. Continue. And let's check what was happening. Okay, it will jump to DE. Now it will jump here and it will work. Let's see. Let's step. Let's step and wasn't the others. Oh, I think I wrote the address wrong or what? Let's see now if I reopen it will jump to CE3. Oh, CE3. Okay, it will jump around here. By a step. Okay, you have the Noxlet. Noxlet, blah blah blah. It might not work again outside radar because of the environment variables, as I said. But I will try anyway. Es que me cago en la puta de... Well, you got the idea. Inside the debugger, we are in the Noxlet, or I don't think that the thing filing is the shellcode. Also has happened to me sometimes. Let's try with CFBB. Okay, well, I don't really care about that. It's executing in here inside the debugger. You should find the address with the environment variables are the same as. The way to do that is checking the core file. Okay, you examine the core file, you will find. But we will do this same exploit, but working next. Not this shit. So well, let's just send it to hell. Now we will do the same thing, but with address randomization in place. Okay, because it doesn't make fucking sense to jump directly to the stack. So what we do it, still we will have the stack will be executable, okay? But we have to enable address layout randomization. So we enable the layout randomization, put the stack into executable, and go to this folder, which is basically the same code. Okay, the code is the same exactly with the dummy function, which does the overflow on a buffer of 64 bytes. So what we'll be doing to jump to that cell code in a good way, instead of jumping by a fixed address which will change with address randomization. We can use Cheetah for it. Okay, so we can open our binary, and then we use call to Cheetah, and here we can say I want jumps to the register ESP, and it only found one, which in fact I put it in there. So well, it will look for jump to ESP, call to ESP, pop, ESP, no, well, many other combinations I don't even remember. So instead of jumping to a fixed address, we will jump to this address. It will be on charge of jumping to the correct location. This will work always. So if we do exactly the same payload as in here, but the address, instead of being a stack address, we add the address of that instruction, it should work, or then I will go home. So one. You can see. Okay. And also now we don't even need to do that fucking nopsless. It's enough use with AP. So it will end up being much more sorted. Okay, there we have. And in here we have the address of the jump ESP instruction and then our shellcode. And as you can see, this works. Yeah, jumping to a fixed address in the stack is stupid. As I told you, it changed so much just based on environment variables. Radar sets some variables. Everyone sets variables. When you forward, it doesn't make sense to jump directly to the stack. Nobody uses that. And well, using that kind of trampolines, you can also overcome address layout randomization, which is stupid because whenever there is address layout randomization, the stack is not executable. But anyway, okay, the next bug will be an off by one. This is also kind of stupid, but I think it's kind of interesting because I can sit in here and speak out everything again and again and drop and show you how to build ropchains and what a stack overflow is and how to write red or how to abuse a heap allocator, whatever. But that won't make you. That one will help you to exploit. I mean, those are only some techniques. What you need for exploiting is to think, because whenever you are exploiting, you have some data under control, some gadgets, some protections. So whatever you have to do usually is, what the fuck can I do with these things to make this shit give me money? Okay, so basically that's the thing. I can show you many techniques, but they won't do a difference. Okay, so this is kind of a stupid bug, but it's kind of interesting because applies this kind of thing that I'm telling you. Can anyone tell me where the bug is? It's really stupid. Yeah. Sí, lo voy a hacer rápido. Where is the bug, Pancake? It's called off by one.
That two functions should be static.
Well,
A string cat.
yeah, exactly.
Yeah.
Many string functions, even if they have a limit, if the null byte, it won't count the null byte, okay? So it will write 256 bytes, and after that it will write a 0 byte in there, okay? So also, well, I don't know if there is a comment in here, but also just note that to build this, I'm using this to align the stack just to multiples of 2. So basically, the base pointer will be next after this, exactly next after this. You will be overwriting just 1 byte of the base pointer. Anyone have any idea how to exploit this? having in mind that address layout randomization is on, but the stack is still executable. No ideas? No worry. Julian? Okay. Basically, if you have, let's suppose that we have this stack, which address space, it grows upwards as always, and the address space grows like always. So we have here the base pointer and the return address. We can only overwrite 1 byte. We'll end up overwriting this. Okay, here you can see the overflow, which we wrote AAAAA, and here the string copy function will add the null byte. So it will just overwrite 0, 0. What happens with this is that the base pointer will end up pointing up back to the stack. So what you can do to exploit this? You have control of this data. And base pointer is pointing here right now. You mean the shellcode? The shellcode?
Yeah.
Just directly in there?
Yeah, you change the.
Yeah, but it's moving only it's only moving the stack, the base pointer. The next thing that it will do will be usually when, let's say, it will make a leave and return. So it will end up executing a return, getting this one of these addresses.
The desired address in.
Yeah, that will be one way, but after that, okay, it's basically the same as before. I don't know if I have a string here. What we will be doing is, because the stack, as I told you, it changed, we don't really know which part of our buffer it will change the base pointer to. Maybe sometimes it will be here, and other times it will be here. Because this time it was, you cannot predict if the buffer will be in this chunk or it will be in this other. So sometimes it will end up jumping in here, other times wherever. Anyway, what we do is spam this instead of with A's, spam it with a gadget for return address. Let me see if I have. What we will be doing is spamming with a red, any red in the binary. In this case, 4 by 1. PD1 0804 484. This is just a red instruction, okay? And we will spam all this with red, 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 red. Because we don't really know. This is a fucking mess of drawing. It will just add reds everywhere. So it doesn't really matter when it puts a zero in here, that it will start to execute red and take the next, which is again a red, and a red, a red. It will be kind of a rope, kind of. And at the end, just before this, the last one will be a jump ESP, I guess. Or, well, not the last one. We will put our shellcode at the end, and here a jump ESP. I think the code is in here. So as I told you, this is an address of a red instruction. this other address is the same gadget we used before, which is a jump to ESP, and this is the shellcode. Basically, you can see this. See? Basically, what we do is put our shellcode in here. Let's call it S8 at the end. Let's point a pointer to jump ESP in here. And all this is spam with a point at the address of a red. So it doesn't really mind whenever it will change, it will override the 0 byte. It might end up in here, or in here. So it will keep doing reds. It takes this one and jump to the shellcode. It's quite a stupid bug. It's really silly, but you can see that even with 1 byte override, sometimes you can even exploit something. Well, you need a executable stack, which obviously you won't be finding. But usually you have to think of creative ways to do things, kind of things. So now this should work, I guess, because if you run that exploit, it exploits. And it says all I can say. The code is in the, I think there is not much more I can say about this. But, okay, which one is next? Well, this is an example using PXR. You can see how the stack was. You can see how the stack was. It's a spam with the address of a red function. All the stack is spam with it. The last one is the jump to ESP, and here we have the shellcode. And as I told you before, well, this is a 0, it will end up around there, I don't know. Okay, next we will make a simple or a small rope. Okay. We will make a small rope, so you can see Rarun. For this one, we have the stack is non-executable, and we have address space randomization or address file randomization on. So the code, I guess, it's the same. One. The code must be pretty much the same one, but it's just that I added some artificial gadgets. Okay, I just added some artificial gadgets, but oh no, it's not the same code. It's another one. Well, the bug is basically it will read an environment variable, which is called input data, and well, it's 20 bytes, and it will copy to a buffer of 20 bytes, whatever is in the environment variable input data. So for this, we will be making a rope which will execute a shell, which I also artificially put in already in the code. And to test this, we can use the rope and the binary we want to check. We want to look for gadgets in it. When it analyzes the binary, it will open a web server, so you can just click on it, and you won't see anything because the resolution is so small that. Okay, that kind of works. That kind of works. So I think I live, yeah. Not this one. Yes. So we want an XB which has, the ID of EX, the ID of the syscall is 0B. The first argument is the CMD you want to run. And ECX is the arguments, the environment variables, and this is not commonly used. Okay, so we want to build this ropchain. So we will start by moving to EAX 0B. And as I told you, there are artificial gadgets that I put in there. So we can do searches in here. And we have here the gadget itself. We can add it pressing the button. And after the gadget, it does a pop. So we need to add some padding. Okay, because it will make a pop. Now we want to put. Okay, I will set to null ECX and EDX. So I will search for X source over ECX. I have a gadget in here, I add it, and it also makes a pop, so I add some padding. I want also to set EDX. I made the search, and here I have the gadget with EDX, and it also makes a pop, so we add another. Well, can change the colors. It's very, very useful. As fruits useful, as Dutch will say. And well, at last, I want to get into EBX a pointer to the command we want to execute. So I will search for a pop EBX, and we have a pop EBX in here. And what it will be popping, it will be the address of of the cell which I also artificially wrote in it. Okay, so let me check. It was str bin sh. Str string bin sh is at this address. We use consider we have bin sh. So we add it. Say as a comment pointer to we add it, and at last we need to call to the interrupt int 80 to trigger the syscall. And well, another of the cool things this has is that you can move actually the places just by drag and dropping. And then also you can debug. You press debug, it will run Radare in debug mode and will set up, as you can see, it will set up the stack with the values you said. So you can debug your rope gadget easily. By step, you will see it's in a red. Sorry, I cannot make this. Yes. I don't know which terminal is it. I think I cannot change the font size, but well, if I step, you will see how the. Okay, this is the fucking bug I told Pancake the other day. But I don't know why at the third or the fourth it works. It's working now. So well, if you step, we are in a red, and now we will be moving to a EAX B in X, pop red, and it will be doing the next one, which is here down here, which is putting an XOR over ECX to set it to 0. Now it's storing edx to put it to 0. Pop EBX to get the shell address, the address to the command, and then call to the interruption. Okay, and well, then that's not a joke, but you can debug your ropchains back with this. You can save this chain in here, and we will save it somewhere, like tmp chain rarop. And if we go with cheetah, we can use pipe. We can open those files and generate C output. You need to paste it, or using on exploiting C. You can use Python, which I don't do, but I think I'm not. I mean, I think this works because I don't do Python, but I think it's the correct syntax. Or you can even use, say, text, and it will do as escape C string of your ropchain. So, well, to exploit this, I don't know exactly what I did. Oh yeah, I just made the same as before. I think it was some padding till you reach the thread address, and then your ropchain in there. You run it, it gives you. And this way you can have non-executable stack and address layout randomization, etc. One quick thing I will show you, but I won't be explaining probably. It's the stack cookies. As I told you before, whenever you fork, you inherit the stack cookie. Okay, so the stack cookie is constant against while the process exists, and it's inherited by all the children. So if you have a network service which is based on fork, even if you kill the child because you failed during exploitation, you make another connection, it will fork again, and you will have the same cookie. So you can brute force. You can make brute force over the cookie. So I have here a stack cookie which has much more code than anything, because I have to make a quick server based on, okay, it's listening for connections. This is the cookie, and so here is the exploit that you can take a look later at the code, and it will just brute force the cookie, as you can see. It has caused many crashes. The child crashed constantly, but each new connection, it will fork again, you will crash it again, so you just have to brute force byte by byte till you find it. It's quite easy, in fact. So you can even perform one famous bug you can apply this was for engines. I don't know if I said it okay, for the web server, where it's based on fork, so you could crash the web server again and again and again, get the stack cookie, and then run your exploit once you have the stack cookie. Okay, I will show you another quick one, which is a format string and also comes with cheetah. I will finish, I guess. Also, well, for Cheetah you have there is a format string helper, okay, which because everybody hates format strings, I do. Whenever you have to exploit them, you forget about how it was working, all the characters and all that shit. So I made a helper that where you specify at which parameter you can read your string, your controlled string. For example, at parameter 4, at which address you want to write at, and for example, I want to write at address 41, 41, 41, and which data you can write, you want to write. So for example, I've been writing 19, and it will generate the format string used for you. You can even perform multiple writes, okay? You can make a file, and you can say, I want to write in this address, this data, at this address, this data, and at this address, this data. And it will generate the whole format string. So you can even write a rope in a memory area, and later do another write to trigger a stack pivot or whatever. So, well, I will do this one, I guess, the last. If the format string, which, as I told you, format, it's just whatever I put as argument, it will interpret it as a format string. Okay, if I say p, it will print a pointer. If I print x, it will print hexadecimal, whatever. So I want to know at which position I'm at. So I will write 4 A's. And for example, I will try if it's what's at the first argument. First argument, okay. Second argument, third argument in the stack, fourth argument, okay. We can see that at the fourth argument in the stack, we are reading our own string. So, the format string is the fourth argument, so we will make pipe theta format position 4 from the fourth argument, and next we will check what we want to write, or where we want to write that. And well, if we check the code, if you check the code, I just deliberately put here an spawn self function. So we want to point or somewhat jump to this function, which is not referenced anywhere in the code. And for this, we can just overwrite the relocation, not the relocation table, the GOT or the PLT. If we take a look after the format string, printf, there is a print also. So if we open the disassembly and we print okay, we can see that we have our format string in here, and after that there is a call to puts. If we check what's in puts, we see that there is a jump, which is what I told you before, that the relocations are done in during runtime for the first time, and it will jump to wherever this address is pointing to. Okay, it will jump to this, whatever data is in this address. Right now in this address, we have, right now in that address we have this, but we will change it. Okay? Necesito otra puta, sí. Yeah. So it was the fourth argument. We want to write that address. What I have done. Yeah, we want to write at this address, And what we want to write in there. What we want to write in there is the address of the spawn cell function. So the data we want to write in there, it's is this, which is the start of the spawn cell function. To do that, okay, format. I forgot to put the command format. Oh yes. Okay, address and data. And it will just make the format string. So now we can use it as first argument. And I guess if you check this run exploit, it has the format string in here. So if we run it, we get shell. So now it's quite quick and quite easy to make any format string. And well, at last, I have been working on a use after free, which is called Tinder, which is Tinder for Radare people, where you can meet other people with your same likes or whatever. So it's so you register in here. I'm Pepe. And well, you can add a bio to talk about yourself, get the bio from another user, delete your account, or list the users. Right now, Pepe is only alone in there. We can create another one. And now Pepe and Braulio are there to have some homosexual love. Anyway, you can delete. There is a lot of code which I have spent like 1 hour doing it. It's shitty code, the worst code I have written in my life, I guess, because I have done it in a Rust. So there are race conditions when handling list, linked list, and a lot of shit. But one of the things interesting is that in your bio, if I set my bio, I can put the format strings. So when I do get bio from Braulio, okay, there is a format string in there, which we will be using to leak addresses, because in here everything is enabled, okay? You have address space, random address space, there is a non-executable stack, there are stack cookies, and even the binary is randomized. So we need some way to leak the address of our binary, and we use that format string for that. And also there is an use after free that I call delete to delete my account. Now my user has been deleted, but I did not log out, and I can still use the delete structure or object. If I do another delete, I will have a double free. It's done. So well, you can take a look at the code at home, etc. But just to see it running, we can in there and exploit the address of the server. Okay, and we have cell. Okay, with all the protection enabled, and you get cell. Also, the code is a fucking piece of shit because it's talking with localhost. So even if you use no-delay TCP sockets, the kernel will still pack your multiple writes in one only read. So I have been adding sleeves, fake sleeves. It's a fucking mess. So just in case you want to take a look to it and have some fun. And well, there is also a format string, and well, enjoy r2con and have fun.